Hey everybody, welcome to Permutations with me. We're going to be counting things when we care about what order they're in. Or said maybe a little bit more mathy, a permutation is a set of distinct objects in an ordered arrangement of the set. So we don't necessarily have to use all of those objects, and so we have something called a k-permutation, which is just the arrangement of k many of those elements. So if we rephrase this, we just want to count the number of ways we can arrange k many of n total things when we care about the order. For instance, if I were to ask how many two-digit numbers we can make from the set 1, 2, 3, 4, 5, order very obviously matters. We could have 2 and 3 could make 23, but it could also make 32, and those are not the same number. So the way we can do this is honestly just stuff that we did from last time. We can use product rule. We can say we have a two-digit number like this, and then we have 5 options for this first number. And then let's think of this set like a bin. So once you take something out, so if we take the number 3 out, we can't use 3. There's no more 3s left in the bin. There's only 1 3 sitting there in our set. So we're not allowing repetition. I can spell repetition. Go me. So that means when we come to this second element, since we took the 3 out of the set already, we don't have a 3 to work with anymore. So now we only have 4 options left. So that means we have 5 times 4, which is equal to 20, many combinations or permutations that we can make with 2 digits ranging from 1 to 5. We can generalize this rule though, so that we don't have to run through this necessarily every single time. In general, if you have n many elements and you want to arrange k many of them, we're not going to say we want to arrange 0 of them, so k starts at 1. Then there are going to be this many permutations from the n distinct elements. The intuition behind this is this top number is the number of ways that we could arrange all of the objects, and then the bottom is the number of ways we can arrange n minus k many after we've selected the k number that we do want. So if I were to prove this, it actually is going to look a lot like the reasoning that we just did for the last problem. So when I look at this, I would say the first element has n many places. I'm gonna move this. It could go. Okay. And then after we pick where that first element goes, now we're on to the second element. And the second element is going to have n minus 1 many places it can go. And then if we just keep running down, so we have k many that we want to arrange. So by the time we get down to k, we have the kth element has, and this is the challenge. The question is, how many places can the kth element go? And I'm going to say, let's look at 1, let's look at 2, and see if we can find a pattern. So when there was 1, we subtracted 0, which is 1 minus 1. And when there was 2, we subtracted 1, which would be 2 minus 1. And so I'm going to say that we're going to have n minus k minus 1. Many places that it could go. And then if we simplify that, that's just n minus k plus 1. And then if you're not convinced yet, do a couple more. Do like the third and the fourth element. All right. So now that we have this, we can do product rule. We just take all these guys and we multiply them together, basically. So the number of choices for the first one, number of choices for the second one, number of choices for the kth one. So that's going to be P nk, which is equal to this guy. And then I'm going to make the observation that we could rearrange everything to look like this, where we multiply all the way down. So n minus k, all the way down to like 1, so that we have n factorial up there. But I have all these guys that I didn't have before, so we're going to divide by those guys. So like that. So then now we have n minus k factorial on the bottom. So that's n factorial over n minus k factorial. And that is exactly the formula that we got up here. Okay. Then quick note, this works when k is equal to n, because then you get n factorial over n minus n factorial, which is n factorial over 0 factorial, but that is not a problem. This is not the same thing as being over 0, because 0 factorial is equal to 1. That's like that. All right, let's run back. Let's use the formula on the question that we just looked at. How many two-digit numbers can you make from a set of numbers 1, 2, 3, 4, 5? So we're going to say we have the number of elements in total that we have is 5. The number of elements that we want to arrange is 2. So we put these together. So we have 5, 2, which is going to be 5 factorial over 5 minus 2 factorial. And then that's going to be 5 factorial over 3 factorial, which is just, if you don't see it, I'll write it out just to make sure. 1, 2, 3s. So that's just 5 times 4 like we had before. And so we get 20. So we're still getting the same things. Awesome. Let's try this on one more example. We're going to ask how many ways we can select a first prize winner, a second prize winner, and a third prize winner if we have 100 different people who have entered a contest. Once again, I have to read into this problem to understand that order matters. If I got first place and you got second place, would be a very different situation than if you got first place and I got second place. And so order is going to matter, so that means we're in the land of permutations. So let's figure out what our n and k are going to be. N is the total number of things that we have to arrange, which would be 100. And then the number of things that we want to actually arrange, we want first, second, and third place. And so that means we have 3. So we combine that and we say P of 100, 3, which is 100 factorial over 100 minus 3 factorial. And then that's going to be 100 factorial over 97 factorial, which simplifies to 100 times 99 times 98, which is kind of, if you look at this sort of a thing again, like Or let's not use that. We're going to draw a winner's block. Like this is 1, this is 2, and this is 3. So you would have 100 choices for this guy, and then after you pick first place, you would have 99 choices for this guy, and then 98 choices for this guy. So again, permutations is just product rule, but we have a very special version of product rule now. If you multiply this all out, it's like 970,200. So a lot of different possibilities. That's all I have on permutations. Again, it is just counting things when the order is really important. You need to read into your problem, and when you're looking at the problem, if you're thinking about like maybe it might be a permutation, ask yourself, does the order matter? If I switch the order, does that like change what this problem means? Like first versus second place, or 23 versus 32, and those sorts of things. Okay, but that's all I have for permutations right now, and we'll talk about combinations next time.